Last summer, there were devastating floods across much of Northern Europe. Over 240 people died, and billions of pounds worth of damage was done. One lesson from these floods was the importance of early warning systems, which doubtless saved many lives. This lesson was reinforced by the tragic case of a nursing home in the German town of Erfstadt. Here, flood warnings put out, but local authorities could not get to the care home in time, and 12 residents tragically died. Although Denmark wasn't too affected by these floods, my partners at the Danish Meteorological Institute paid close attention to them. They're the designated national authority for putting out flood warnings, and they have early warning systems in place for coastal floods and extreme rainfall events. But for river floods, they only have real-time indicators of the river flow, and they don't have models that predict the flow ahead of time. So my name is Yann, and for my faculty project, I partner with the Danish Meteorological Institute, DMI, to explore the development of an early warning system for river floods across the Danish rivers network. Since the primary aim of this project was to guide the future development of DMI's flood warning system, I first wanted to assess the feasibility of building a simple river flow forecasting model based on DMI's existing data sources. I then wanted to assess the importance of the different data sources that DMI had available to them for informing river flow forecasts. And then I wanted to understand the chosen forecasting approach, how that would perform across the entire Danish river network. So first, let me take you through the data that I had available. For each river measuring station, I had hourly measurements of the water flow, the amount of rainfall, and the temperature. I also had daily measurements of the evapotranspiration rate. This is a measure of how much moisture is taken up into the atmosphere, and I had information about the river basin, such as catchment area size and soil type. We have this data over around 300 stations, the yellow dots in this map, and over 10 to 30 years, depending on the particular station. For my approach, I began with some exploratory data analysis, looking at the temporal correlation between precipitation and river flow, for example, and then this informed the features I engineered to feed into our model. For the model choice, I tried models of different complexities, from linear regression through to deep neural networks, which had been used before in river flow forecasting. The model that I settled on is a gradient-boosted decision tree model called LightGBM. The advantage of this model is that it's relatively fast to train, it's lightweight, and it's easy to iterate over quickly. And it was also easy to sort of dig into in using SHAP feature importance to understand what data was making the predictions or impacting the predictions the most. So how does LightGBM work? Well, the basic element of this model is a decision tree, which I'll illustrate here. It's like a game of 20 questions, which interrogates the data available to it. So in this case, it first asks whether it's been rain. If it's rain, then it asks whether it's below freezing or above freezing, because the river might be frozen. And based on that answer, then asks whether there's high upstream flow or not. And based on that answer, it might predict whether there's a flood or not. So that's how a decision tree works. And LightGBM part is just basically taking a bunch, is a sophisticated way of taking a bunch of these decision trees and coming up with an overall prediction. And in this case, the prediction is flow forecast 1 day ahead. So my next step was to train a different model for each of the river stations that I had sufficient data for, with the goal of predicting the flow 1 day ahead of time. In this case, we look at the Gudenå River, which I've highlighted in this green box here on the map. So February 2020 saw floods all across Denmark. And so the black line here shows the observed flow, and the green line shows the prediction. And in this blue shaded area here shows the amount of rainfall that happened over the last day. And so the model predicts that there would be a big increase in flow. And indeed, this is what our observations show as well after that. And if we keep going over the entire month, we'll see that the forecast does pretty well at predicting the flow in the next day for this river station. So what's important for a hydrologist, however, is not necessarily how well the model forecasts over the entire flow part, but how well it does at giving advance warning for the peaks. So I assess the model performance by assessing how reliably it gave an advance warning of these and how accurately it predicted the high points. So this is another river, the Gudenå River, which we see does fairly well in the low bits, but doesn't do that well in some of the peaks. It doesn't give good advance forecast here. And so this kind of shows the importance of the metric. And so with this metric in mind, I'm going to look at how well my model performs across the entire river network. And so 12 hours is it's the advance warning that the UK Environment Agency recommends for emergency services to evacuate an area. And this map here shows how much advance warning there is for each of the 174 river station models that I trained. The deeper the blue, the more the advance warning. So 42 of the river stations, or that's around a quarter, can provide 12 hours of advance warning with 82% peak flow accuracy. So to summarize, if we return to our initial objectives, I tested the feasibility of building a flood forecaster with existing DMI data and found that a simple light GBM model works very well for predicting forecasts flow 1 day ahead of time. I also assessed the relative importance of DMI's data in making these predictions. We found that high quality flow history and rainfall were the most important sources. And finally, I found that a simple model worked quite well across most river types and could entail the first step towards an early warning system. Thanks for listening.